So here's an example of a pedigree question that would use this type of information. So here's a rare condition, which you would be familiar with from earlier on in the course. We have an affected daughter of two unaffected parents, so this is obviously something that is autosomal recessive, which again should be familiar from previous work in the course. We have new information now, though. We know that the fitness of this genotype, the little a genotype, has a fitness of 0, so these individuals survive, but they're not capable of reproduction, so perhaps it's something that causes sterility, which would take their fitness to 0. And the incidence in this population is 1 in 10,000 live births. Now, normally, if you were asking the question, well, what's the probability that, let's just put the generations on here, what is the probability that 3-1 is affected, little a, previously in the course you would simply say 0 because you would be assuming that this individual marrying in would be homozygous dominant, big A. And the reason for that is the assumption was based on it being a rare condition, the probability that they're a carrier is unlikely. Now, however, with this information, we have the tools we need to calculate whether or not this individual is in fact a carrier or not. So that's what we'll do now. So the probability of this individual being a carrier should be straightforward from the pedigree. So we can't be certain what their genotype is. We know they're not little a, so as a result, their probability of being a carrier is equal to 2/3. And again, that should be familiar from previous work in the course. Okay, so we're not going to review that here. Okay, now the question is, what do we do with this individual? There is now a non-zero probability that this individual is a carrier, and we have the ability to calculate exactly what that probability is. It's going to be close to 0, but it's not going to be 0 per se. So as we did before in the previous video, we can use this logic. In this population, if there's an incidence of 1 in 10,000 births for this condition, then we know that that is 1/4 times the frequency of being a heterozygote times the frequency of being a heterozygote, which gives us 1 in 10,000. Okay. So what that means is the frequency of being a heterozygote all squared is equal to 4 out of 10,000. Okay, so now we're just using algebra, and I've simply multiplied both sides by 4, and I've expressed this as the frequency of the heterozygous clasp, and because they're multiplied with each other, that's where that square comes from. So if we carry that further, that simply means that the frequency of the heterozygous class is equal to the square root of 4 divided by 10,000. And if you work all that through, what you should find is that the frequency of the heterozygous class is 0.02. So now there's actually a 2% probability that this individual is actually a carrier. Now, the other thing that you need to remember, however, if we think about it, this individual here, that probability value that we just calculated, I'll just move that over so I have more space. So that being 0.02, that also comes from a total population where the probability, the supposed probability of this individual being little a is also not 0. So this would be 1 in 10,000. Now, I know that doesn't make sense because this individual is reproducing, obviously. He and his wife are expecting a child. So this person cannot be little a. But this value assumes that this is still an option. And then the remaining option you would have to calculate simply by adding these up and figuring out what this is. So what the point I'm making here is we know that this is not an option. So we actually need to normalize. So the actual probability of this individual being a carrier is 0.02, now normalized to the only possible options, which is simply 1 minus everything that we can exclude, just as we've done with normalization before. So this value isn't going to change very much. because 1 minus 1 out of 10,000 is not a very large value. So this is going to be very, very close to 1. So because this is so close to 1, this is such a small value, it doesn't shift much from 1. So the actual probability is not going to shift very much from 2%, but it's still, for completeness, you should complete this step and do the normalization. So once you've calculated that value, and it will be slightly more than decimal 0.2, only very, very slightly more, because this is such a small value and we're subtracting it from 1, so this isn't going to be much different from 1. But you'll have a value for the probability that this individual is a carrier. Now that you have that value, you can plug that into the requirements, just as we've done for pedigrees all along. So what does it take for this individual to be little a? Well, the mother needs to be a carrier, probability 2/3. Dad needs to be a carrier, probability slightly more than decimal 0.2, whatever that number actually is. Mom needs to pass the little a allele, probability 1/2, and dad needs to pass the little a allele, probability 1/2. So those 4 terms multiplied together will give you the final probability that their unborn child will be affected with the condition. Now, if I ask you a question such as, well, what's the probability this individual is a carrier and not homozygous recessive, things like that, then you would have to do one of those branch diagrams like we've done before, where you've got, say, the mother has a probability of 2/3 being a carrier, 1/3 being homozygous dominant, and then the dad would have a probability that's slightly more than decimal 0.2, so whatever that actually is when you do your calculation of being a carrier, and then whatever the equivalent is for being a big A, so 1 minus this value for this value here. And then you would do the branch diagrams just like we've done before to determine the actual probabilities of all the different outcomes. You would effectively have a mating between 2 individuals that you're not certain of their genotype anymore, so then you would have exactly that same setup that we dealt with earlier on in the course, where you do the probabilities using that type of flow diagram. In the case where I'm specifically asking what's the probability of this individual being affected, being little a, then you can simply do it as a string of probabilities, because there's only one way for this individual to be little a. Mom has to be a carrier, 2/3. Dad has to be a carrier, slightly more than decimal 0.2. Mom has to pass the little a, assuming she has it, probability 1/2. Assuming dad has the little a, dad has to pass it, probability 1/2. And because we say all of those things have to happen in sequence, 1 and 2 and 3 and 4, we use the product rule to multiply them all together to arrive at the final probability that this individual is affected, just like we have done before in the past. So this information, the fact that we are dealing with a rare condition, but we now have information about the fitness and the incidence in the population, allows us to assess the probability that individuals marrying into the family, who are not related, but marrying in, perhaps might be carrying that rare allele. And it allows us to determine the exact probability that they're bringing it in.